Okay, so we're continuing on the discussion about some linear algebra review, and we finished off a little bit of our matrix review up there in the last video. So now we wanted to talk a little bit more about vectors, and in particular the inner product. Okay, and so given two vectors, so a vector, you'll remember, for us, a vector is just defined to be a column of numbers. You'll notice that that is different than how you would define a vector in physics, right? In physics, you would define a vector as something with magnitude and direction. But for us, a vector is just a column of numbers. So typically a vector, if I just write x as a vector, right, you can assume that it's a column vector. Okay, and so what I wanted to talk about, was the inner product. And so we know what the inner product is, right? So if x is x1 through xn, and y is y1 through yn. Oops. Uh-oh. Sorry about that. I had a Windows update interrupt me there. Let's see if we can get through here before we get that updated again. Okay, so x, the inner product is going to be defined. This is another reason why I wanted to do this, is just to define this notation with the parentheses. X comma y, when they're vectors like this, is defined to be the inner product. Now, if we define this as multiplication, you could say it's x transpose times y, right? And that's going to be, if you write it out, oops, that's x transpose times y, right? And so that's just going to be the product, but then you add them together, x and yn. Okay, so you're taking the product element-wise between the two vectors, and then you're summing the rest, summing the numbers together. Good. So this is going to be a scalar, right, that comes out of the inner product. And the reason I wanted to bring this up is because if x or y or both are complex, then the inner product's a little bit different. For complex vectors, x, y is actually defined to be, how do I want to write this? Well, let me rewrite it this way. It's going to be the sum, I equals 1 to n, of xi, yi bar. Okay, so that means you take the dot product of the two vectors, but you have to take the transpose, or it's not the transpose, the conjugate of y first. Okay. By the way, why would you do that? Let's just take a quick example. How about if x is 1 plus I and let's say minus 2 minus I. And let's take the inner product of x with itself. Okay, so that would be, you would go ahead and take this 1 plus I, minus 2 minus I, and then you would multiply that times the conjugate of the other. That would be 1 minus I times minus 2 plus I. And do you see what you get? You get 1 plus I times 1 minus I plus the minus 2 minus I times minus 2 plus I. And so these become real numbers, right? That becomes 1 squared plus I squared, and this becomes minus 2 squared plus I squared. Oh, minus I squared. Sorry about that. Oh, I should have put a number. Oh, well. The idea here is that you get to 1 plus 1 there, plus 4 plus 1. Yeah, okay. I kind of messed up my thing here, but 4, 5, 6, 7. Okay. Let's see. And so x and y are orthogonal. If and only if the inner product between x and y equals 0, right? And that's true for complex as well as real. Let's see, the length of a vector is the magnitude of x, right? And that's going to be the square root of the inner product of x with itself. Or you could write that as the square root of x1 squared plus xn squared. Good. And then let's see, what else do we need? Identity. The identity matrix. The identity matrix is the matrix with 1s along the diagonal, 0s everywhere else. And so typically the identity will always be square. So we only need one. Let's see if I can write this, in. And we'll assume that that's an n by n, right? So square matrix. Good. Invertibility. So to find the inverse, do we remember how to do that? For general matrix A, we construct the matrix A and then stick on the identity matrix, and then we do row reduction on A until we get to identity on this side, hopefully, and then on the other side will be A inverse. Okay, so that's generally how you construct A inverse, although we know that for a 2 by 2 matrix, we know that there's a nice formula for A inverse. Do we remember what that is? Sure. Let's one over the determinant of A. And then you switch these and negate those. Good. All right. Okay, so I am kind of rushing through this last little step here. The last thing that I wanted to just mention in passing, and I'm sure you remember all this stuff, is it's when we, in Calc 3, we talked about vectors that are actually composed of functions of time. So we might have x1 of t, x2 of t, and so on. Okay, and so we might also have a matrix that is actually, instead of having real numbers, we may have functions, f1 of t, or maybe f11, f12 of t, and so on, f21 of t. Okay, fmn of t. Okay. And then the reason I bring this up is because we can actually integrate and differentiate in kind of the obvious way. If you take the derivative of a vector of functions, that's actually done component-wise. And same thing for a matrix. You could take the derivative of the matrix with respect to t, and you would just do that component-wise. So all the functions you would just differentiate to get the derivative. And so, of course, what would you do for the antiderivative? For the antiderivative, we could do the same. So this would also, the antiderivative then would be done component-wise as well. So when we're when we're working with vector functions like this, we can differentiate and anti-differentiate just as usual. Good. And finally, there's kind of an interesting note on the last page, page 371, where some of the rules of differentiation are mentioned there. And so those are kind of fun to take a look at. And so that's it for now. Tonight's homework is going to be pretty short. It's mainly just to get you into some review of linear algebra, and just to remember what some of the notation is. And also, we'll try doing a little bit of homework. We'll try uploading something for homework before our next class session, just to be sure that everybody's got that nailed down. All right, so I guess that's it for now. I will see you later. Our next section will be a little bit more into the linear independence and eigenvectors and all that kind of stuff from linear algebra. Okay, I'll see you then.